All right, so before the break, we were taking a look at logistic regression. We developed the whole motivation for it, why log likelihood is what we try to maximize, okay? And to convert it into a minimization problem, we simply put a negative sign over here, right? And then we try to find the parameters beta that will give us the best result for all the training data, right? So all the derivation that we talked about, I've already put it on the website. Okay, so the link over here is logistic regression. Okay, so anyway, try, exactly just like we did on the board. These x of I, all of these I1 through n are the features, beta are the coefficients, and the hypothesis is, to multiply the betas with the features and produce an output, and to convert it into the probability as we discussed, we pass it through a sigmoid. So once we get, so over here I called it sigma of g, but it could be, f of g or whatever for h of g. Anyway, in matrix form it is beta t x of I, as we discussed, right? Okay, so then we are trying to enhance the individual probability when the target class or the expected output is 1. Also trying to enhance the probability when the expected output is 0, which will be written as 1 minus the h of x of I, right? And then both of these could be combined in one term, as we discussed, by this equation 5 over here, h of, right? As you saw, if yi is 1, then it will be, this will be 0, this will just become 1, and the result will be just h of x of I, and vice versa. If yi is 0, this will be 1, and just 1 minus h of x of I, which is basically this equation 4 over here, right? Anyway, so exactly, and I've tried to give as much explanation, so even if you didn't follow it, as you go home, try to go through it, see if everything makes perfect sense. And then as we discussed, the maximum likelihood, which is the product of the individual probabilities, is prone to numerical errors because it could easily become very close to 0 because all probabilities are less than 1. So if the number of training data, which is the m over here, is large, that will happen. And so in practice, rather than trying to maximize the likelihood, we try to maximize the log of the likelihood. And the log will change the product to a summation. And obviously this goes over here, just like we discussed. And then we can turn this into a minimization problem, okay, by simply putting the negative sign before it, right? So if we can find out partial L divided by partial beta, then put it in the gradient descent algorithm, we can solve any problem. Okay, so like I said, anytime there's a minimization or maximization problem with respect to parameters, we compactly describe it as an equation using argmin or argmax. So once again, that means minimize the log of the likelihood, which is a function of beta, find out whatever beta minimizes it, and that is our goal, right? Okay, and because there's a log involved, this becomes what we call a transcendental type of equation, so there's no closed form solution. Gradient descent is the approach. And as you can see, as we discussed, this is the general form of the gradient descent, beta equal to beta minus alpha. Alpha is the learning rate. The inverted triangle is the gradient or the partial derivative. Okay, just like I said at the bottom, right? Pretty easy. Okay, so then, just like we did on the board, before we take the partial derivatives, I took the log And because we are going to take the partial derivative with respect to beta, see, if you simply take a look at an h of x of I, you may not remember how is this related to beta. So that's why before we take the partial derivatives, I substituted h of x of I by its value in terms of the beta. And then if we take the log, just like we had part 1, part 2, so if we can do partial 1 over partial beta, partial 2 over partial beta, we'll have an easy final solution. So partial 1 over partial beta we already derived just before the break. And if you see over here, this is what we came up with, correct? Okay, yixi 1 minus h of xi. Very similarly, okay, if you go through, and again, there's nothing complicated over here, simple u over v type of derivative involved over here. So if you do partial 2 over partial beta, adjust the terms a little bit. Okay, so I gave all the steps as part of your learning. Just don't take a look at how I did it. Try to do it yourself. See if you can come up with the same answer as I did. Okay, so for the second part, the answer will come out to be something like this. And over here you can see this can be canceled with this one, because this could be written as minus 1 minus h of x of I, right? Okay, so by adding a minus term, so anyway, I did that later on. So now if we try to put both of these two together, here's how the neat thing is. The final answer, take a look over here, is very neat. Y of I. Okay, so first take a look at this part. Y of I minus h of x of I times x of I. So what is y of I once again? The target or the expected output. Okay, so if somebody had diabetes, y of I will be 1. If somebody did not have diabetes, it will be 0. If it's a diabetes type of data once again, right? Okay, so x and of I are our features, right? So again, if there are 10 features, this will be a vector of size 10. And what is h of x of I? If you take a look, this is the sigmoid of, right? Beta 0 plus beta 1, x1 plus beta 2, x2, and so on, beta n, correct? Xn beta n. Okay, so how will we build this thing? From computational point of view, as you can see, we're adding everything, right? So isn't there a summation unit over here? And all of our input features, x1, x2, xn, are our features. And what are they being multiplied by as they go into the summation? Which in this case we're calling beta 0. Beta 1, beta 2, beta n. And there's also a beta 0, so we could write it like this. You guys agree? Then what are we doing? Passing it through?
Activation function. That is
a sigmoid.
Yes.
Isn't this what we do in a single neuron? So logistic regression is essentially same as a single neuron, with the activation function being a sigmoid. Whereas in a neuron, we can use many other activation functions. Once again, why do we have to have only sigmoid as the activation function? There's also an activation function called tan hyperbolic, which, if this is x, produces minus 1 to 1. Negative data, if it's a large negative data, output of the tan hyperbolic would be -1. So my question is, can we use tan hyperbolic in logistic regression?
I mean, it's not well fitted because you're taking a probability, the probability between 0 and 1. Why would you go to -1?
So tan hyperbolic does not make sense.
Yeah, doesn't make
Okay.
sense.
Okay. For logistic regression, for a neural network, where the loss function, see, the key thing to remember is when we did this whole derivation, right? The whole derivation was probability based. If you go back over here, where did I put it?
A little higher.
Right? So we started out by this. This is the probability when the target class is 1. And obviously, once we combine this, the minimization of this is, or the maximization with respect to beta, or the negative with respect to beta, right? So anyway, the whole concept over here is to treat it like a probability problem. We want to maximize the probability of correctly classifying the data. So that's why tan hyperbolic does not make sense. Sigmoid is the one. But if there is some other function that varies from 0 to 1, you could use that as well, right? But sigmoid is the most popular one. So anyway, coming back to the last part over here. Okay, so in our case, as you can see, whatever output it produces, that is h of x of I. Do you guys agree? This part? Right? That's the definition of h of x of I. Pass it through the sigmoid. Okay, so when we deal with neural networks, and I'll do another mathematical development with you guys. Okay, everybody has a slightly different terminology, but I believe, if you follow the way I will develop, intuitively as well as mathematically, it will come out a lot cleaner, it will make a lot of sense. So what I do is, there's an expected output, which I will always represent as a y. So y is the expected output. So this will always be either 1 or 0 in a binary classification, no value in between. Okay. Or y of I, based on a given x of I, there will be a corresponding y of I, right? Very similarly, after the model is trained, or even during training, as we feed in one of these inputs, okay, as we feed in, it will, based on the parameters, it will produce an output, right? Output could be 0.23, output could be 0.89. It will never be 0 or 1. This is what actually it is producing. So I will call whatever output it produces as A of I. What is A? Actual. So essentially what I did is, because we want to minimize this over all m training samples, so y of I minus h of xi became A of I, right? Multiplied by x of I. So this is the derivative of the loss function with respect to beta. And now let me show you, when we program it in Python, this is what we will be programming. So once again, in our Python implementation, let me show you how will we determine the beta. Okay, so remember our algorithm is initialize beta, okay, to whatever randomly. Then we'll go into a loop, right? And we will say beta equal to beta minus alpha, partial L over partial beta. Okay, so alpha, like I said, is the learning rate. We'll fix it, for example, 0.1. Now take a look at partial L over partial beta. How will we compute it? See if you take a look over here. It is the target output. So pretend you picked one data point. So again, let's pretend, let's make it easy. It's a diabetes classification problem. And let's say we only have 3 features. So let's call them X1, X2, X3. Okay. Again, this could be the height of the person, weight of the person, whatever glucose level or whatever could be the third, right? So somebody will give us, okay, for example, this could be 155. This could be, let's say, sorry, this is the height. Height, let's say, if we convert it to inches, let's say 63 inches or 68 inches, whatever, right? This could be the weight, 152. Okay, this could be the blood glucose level, 112, whatever, right? So based on this, suppose the expected output for this known data happens to be 1, meaning the person has diabetes. Okay, suppose somebody gives us another data. Weight of the person, the height of the person is 65 inches, weight is 145, glucose level is 81, expected output is 0. Person does not have diabetes. Okay, so anyway, this way, suppose we're given 1,000 data, 1,000 sets of data, right? So take a look over here, how will we compute partial L over partial beta? For each one, do we know yi?
Yes.
Do we know the actual?
In computer.
See, we'll randomly initialize it, right? We'll feed in 63, 152, 112. We'll pass it through the sigmoid, and it will produce some number. And we multiply it by, so this is a vector multiplication, by the way. So anyway, we'll get a number, and we add it for all the 1,000 samples. And so that will be our partial L over partial beta. So then we'll go plug that value and keep it, right? Okay, so let me show you the Python code. And like I said, Python code only focuses on what is the equation for partial L over partial beta, right? And as we are updating the beta, and if we try to plot the loss function, you'll see the loss function will continue to decrease as it's learning the correct parameters as we keep adjusting them, right? So let me quickly show you now the Python implementation. And I'll give you the Python implementation, but then I will ask you in your next assignment to slightly vary it. So anyway, whatever the change I need in the assignment, I will let you know. So open the project. Okay, so anyway, like I said, you'll get this code on the website, hopefully later today, at the latest tomorrow morning. And so basically what I did is I created a Python class over here. I called it utilities, utils. And here I wrote a couple of functions over here. The purpose is to initialize some data. So once again, this is a binary classification problem. Okay, so the data in this example is basically 2 features only. And the reason I picked 2 features is because we can visualize the data in 2 dimensions, right? So basically, let's say we have O's and X's. Okay, so if the data belongs to the O category, the Y will be 0. If it belongs to the X category, the expected Y will be 1. Okay. Later on, some of the data sets we'll be playing will come from the Excel file. So how do we read the data in Python using a comma-separated Excel file? So here's the code. Anyway, the bottom line is this will read all the data, meaning what is the X coordinate, what's the Y coordinate, and what is the expected class for that one. Okay, so this read data function does a reading of the data from a CSV file. Then I wrote another function where we can randomly generate the data, which is a little more, the first example is linearly separable, as I will show you as I run it. So in fact, let me run it first so that you can see what is the goal over here. So this is, by the way, how the data looks like. As you can see, can we draw a straight line to separate this data?
Yeah, we can.
But you'll see it won't be 100% accurate, correct?
No.
Because as you can see, there are some outliers, or the nature of the data is such that it is not linearly, meaning cannot be separated by a straight line. So anyway.
Even if it's a curve, it would be like overfitted if we were trying to do it.
Okay, so the same data, the green is the decision boundary that we learned through logistic regression. Okay, and as you can see, some of the data is misclassified, right? But supposedly that's, and some of the blue data is misclassified. So the best accuracy that we got is 84% over here. If you play with it, how many times you have to iterate, it might get better. Okay, so if I go to the main over here, okay, so this was based on the random data, which was difficult to separate. So if I comment this out, oops, sorry. Let me try to, if I comment this out. Comment this out, uncomment this out. So if I'm reading from a CSV file, so that data, as I will show you, is a little more separable. So you can see it does a nice job of separating the 2 classes over here. So green is the decision boundary, right? Okay, so as I give you the code, your goal will be to go through, if you're new to Python, get better at it, right? If you're completely new to Python, as an example, if you go to the kiwi.bridgeport.edu, under the handouts, okay, there is a Python tutorial over here, so that if you know C, C++ or Java, you can very quickly learn what are the key concepts over here. So anyway. So how do the if statements look like in Python? How does the for loop look like? How do you create a project using Visual Studio? If you're using Visual Studio, if you're using some other IDE, it's up to you. Okay, anyway. As you get this code, let me go back to the code. So typically what I do is I try to make it object-oriented in Python so that all the reading of the data will go in a separate class. Okay, so with simple functions like utilities over here. Read data random, right? And if there's any plotting involved, how do we plot using matplotlib? So, again, try to study the code. If you have any questions, stop by, see me. Okay, then here's the main code over here. Okay, so I broke it down into simple functions over here. You can see, because remember we're dealing with vectors. So NumPy library allows us, so take a look over here, see if this makes sense. Remember we wanted to implement e to the minus beta transpose x, right? So beta is, let's say, an n by 1 vector. Then beta.t in Python will give you the transpose. Okay, and then np dot will multiply the x vector with the transpose. And finally, np.exponent will do e to the minus, and then pass it through the sigmoid. So anyway, I tried to write it exactly like how we did the mathematical development. For example, if you recall, partial L over partial beta was something like yi minus a of I, x of I, correct?
Yeah.
Okay, so if you take a look over here, ai minus y, and there was a negative sign before, so anyway,
Yeah.
so hopefully this should match. So anyway, that will do partial L over, this function will do, this is just so that as we are going through many iterations, we can see how the log loss is getting bigger or smaller. So again, the two terms over here, so exactly. And if you take a look at the gradient descent, okay, we basically initialize the beta randomly in the beginning. And then we go into a loop and we keep updating the beta, as you can see. Just like we said, after it is trained, if we wanted to give it some unknown data and find out how is it predicting for class 0 or class 1. So I put one more method over here, compute prediction. Anyway, it's a very simple, not more than 100 lines of code. So tonight I'll put it on the website, hopefully, so please go through it and try to learn it, right? We have, if I can go for 10 more minutes, so if you can turn the light on. Okay, so once again, what's the difference between logistic regression and a single neuron network? Okay, so what's the difference? As you guys saw, both of them have a summation, an activation function, right? Okay, so x1, x2, xn, for example, right? And one bias. Okay, in logistic regression, once again, activation function is always sigmoid, whereas in a normal neural network could be anything, right? When we did it, we used beta 1, beta 2, and so on as the model. But could we have called it W1, W2, W3, just like a normal neural network? We could have, right? Reason I again picked beta is because remember, logistic regression comes from the statistical world. There, people do not know what neural networks are, so they use beta as the model parameter. But they are equivalent, right? So now there's one more difference. The loss function over here in logistic regression was what? This was, if you recall, it was the log of the likelihood, or negative of the log of the likelihood, right? So whatever, you know, h of x of I, yi plus 1 minus yi, sorry, 1 minus h of x of I. 1 minus y of I. There was a log over here. Anyway, whatever that was, there was a log of over here, right? And then we put a minus sign to convert it into a minimization function, right? Okay, so the loss function is different in logistic regression compared to a normal network. In a normal network, we could use the same logistic regression loss function, but typically, okay, so we can use logistic regression loss function, but let's say typically we use least square. Okay, so very quickly, remember in our terminology, what do we call the output of the summation?
S.
S. What do we call the output over here? A, right? Okay, so now let me do another quick derivation. It will take me 5 minutes. So here's our loss function. Okay, suppose this is capital L. So in the loss function, we'll feed in y of I. If for a given input of I, the output, so this is S of I, A of I. Okay, so like I said, the loss function typically will be summation 0 to m, if m are the number of inputs, ai minus yi squared. So we try to minimize the error between the actual output and the expected output, right? And typically we put a half over here, which is not important. Even if you don't put it a half, it will still work. Reason we put a half is if we take the derivative, 2 and a half will cancel, it will come out to be a little closer, right? Okay, so our goal, once again, is like in logistic regression, what was the goal? To determine partial L over partial beta. You guys agree? What will be the goal over here? To determine what? Partial L over partial W. And pretend W is, you know, W1, W2, W3, and so on. Okay, so we have to determine partial L over partial W. So now let me give you a very powerful way of computing the partials, especially when neural networks are involved. So here what we do is we basically rely on the chain rule.